Hi everyone, are you able to hear me clearly and see my screen clearly? All right, so today we are going to discuss the transformation part pipelines. This is where we left yesterday. Do we have questions before we start? Great, great. All right, so let's start with the discussion. Wonderful. Great to have all of you in the session. The others are joining, so yeah. So there's a question regarding feature scaling. So do you have a specific question on what does it mean by feature scaling or how? Okay, all right. Yes, Balaji, go ahead with the question. Okay. Could you explain the importance of categorical and numerical transformations? Okay, so basically, most of the algorithms need numerical values, right? And uh, and that too, the algorithm that too, it's better to feed the data to algorithms within a certain range, right? So, right? So that's what we did with the numerical attributes, as in we did the feature scaling for the numerical attributes. All right. Then with respect to the categorical attributes, basically, when you have these strings like in the data saying this is low, this is high, this is very high, this is very low. So instead of having these strings, the text in the data, we convert that to numeric. Okay, so that's what we did in case of categorical. So instead of there were two ways to convert categorical attribute. One was normally converting each value to a number. Other was to convert it like a matrix. Okay, so using the one hot encoding. All right. So that's what we did, the transformation. The importance of both is at the end of the day, we would like to feed this data to algorithms. All right. Okay. Another question was related to correlation and regression in details. We will go into that detail individually. There are individual chapters that are coming up after the project. Question from Bentao, how to develop, create an algorithm that we will learn as we go ahead. Okay. In this session, we are going to focus more on getting started with the entire project. All right. And then we will focus individually on algorithms, on individual algorithms. Okay. Now, question from Kamal. In the fourth step in the checklist, prepare the data for machine learning, but it has many things to take care. That's right. That's right. So, okay, that's right. Okay. So that's right. So we'll try to make a sub checklist of the checklist, and that will give you an idea. Okay. Okay. What is the difference between norm, distance under zero, mean, and unit variance? Okay. Okay. Let me explain what does it mean by feature scaling. In there were we talked about this kind of a feature scaling whereby we converted this kind of a number line into this kind of number line, right? If the value is 100, the first value we convert into 0, last value we convert into 1, and everything in between, the midway. Okay, so the second thing that we did was that is max scaling, but because the data could be condensed or very um, very close by to each other in certain range and could be very sparse on the other range, then the min max doesn't work. Okay, min max doesn't work well. Therefore, a better way of feature scaling could be standardization. Okay, what does standardization do? In the standardization, we first compute something called standard deviation. What does standard deviation do? Standard deviation represent how spread out our values are. If the values are varying from 0 to 1000, the the if the values are varying from 0 to 1000, the variance also will be really high, really high. It'll be more than 1000. And if the values are varying from 0 to a million, the variance would also be somewhere will be more than a million. Okay, so I mean the standard deviation will be more than a million in if the values are varying from 0 to a million. Okay, so basically if we subtract the value from the mean and divide by the variance, we will get a ratio which will be within one mostly. Okay, which will be within one or within two or something like that. So all right, now okay. Sorry, actually, I was talking about variance, not standard deviation. So standard deviation basically would be within like 3 or 4 times of the actual value. So the standard deviation is a good way to see how well our data is spread out. Okay, so what we do in case of feature scaling of in the standardization, we basically subtract the value from the mean and divide by the standard deviation. Similarly here, we are subtracting the value from the mean and divide by standard deviation. So for any data, first we need to compute the standard deviation. First we need to compute the standard deviation, and we also need to compute mean that is anyway required for the standard deviation, and then for each value we could feature scale. Okay. All right. Now, let me go ahead. So what we noticed was that in case of standard deviation based scaling called standardization, features are rescaled so that the output have the properties of standard normal distribution. Okay, the output after we basically scale it, what's going to happen is it's going to convert it into a normal distribution. Even if it was not normal distribution earlier, it is going to convert it into a normal distribution. Okay, it means that when we subtract all the values from the mean and divide by standard deviation, the resulting values are going to have the same behavior as the normal distribution, such as zero mean and unit variance. Okay, meaning if you if you compute the standard deviation of all of the data, which is the result of scaling, after scaling, if you compute the standard deviation is going to be 1. Okay, standard deviation is going to be 1. Okay, so yes. So what was the next question? Next question is related to the session on December 29. Okay, okay, that's something we need to decide. So the on the last day, as in December, so for Indian time, the next Saturday and Sunday is on December 30 and 31. Okay, and therefore, December 31, the second session of the next weekend, is going to be off. But the first session I plan to keep. I hope that is okay with all. The session on next Saturday or next Friday for Binta, so that I want to keep. And the next the session on next Sunday, which is Saturday for the people from US, that one we will keep it off. Okay, is that okay with you, or you? I mean, who all will be attending the next next Saturday morning IST session? Yes, kind of. Yeah, I want to keep the next session on, while next to next I will keep it off. Okay. All right. Yes, Kamal. Yeah. Better way to ask is who cannot attend the next session. Okay. Let me rephrase this. Next session. Okay, which is Saturday in IST, and Saturday morning in IST, and Friday evening in EST. Okay. Who may not be able to attend. Yes, of course, you will receive an email confirmation after this. Okay. All right. So yeah, there'll be only one session next week. All right. Okay. So Tanmay, will you be able to attend the next session? My question was that will you be able to attend next session Saturday? Will you know? Okay. For Noor, Noor will have to cancel the plan for next for the holidays. And Tanmay. Okay. I think a better would be that. Okay. Yeah. Okay. I think I'll just send you an email after the session. Okay. I think I'll just send you after the session. That'll be easier to take a call. Okay. All right. Great. Great. So let's start with our usual discussion, and we'll talk about. Maybe I'll just drop an email after this. That'll be easier to take a call. Great. Let's move on. So this is something that we learned, and moving on. Okay. So any other questions before we start? If the actual value, a good question from Ross, if the actual value y used in training is scaled, do you have to convert the standardization value back to the actual value to interpret the prediction? Yes, that's right. So let's say the house, what is it, what is it that we are trying to calculate as a result of our model? What we are trying to predict is we are trying to predict the median house value, right? Median house value. And in case the median house value has been scaled, has been already scaled, then we will have to unscale it at later point of time. Okay, and how do you unscale it in case of standardization? You do reverse of it. You multiply the resulting value by standard deviation. Okay, by standard deviation, the older one, and then we add the mean to it. Okay, now Question from Neo is, how did we get 1800? Here, um, 1800 was the actual value. Okay, this 1800 was actual value, and we had computed. So imagine that there are many students whose marks are listed, So what we'll do is we'll first compute their mean, then we'll compute the standard deviation. We subtract each value from with the mean, and then divide by the standard deviation, so that all of the scores of all the students in the class will be scaled to something between 0 and 1 or very small values. Okay, all right. Okay, the quick recap is that what was the quick recap? Can I do that quick recap? One is that we converted. Okay, all right. So the first thing was we learned how to handle the missing values. Then we learned how to handle the text categorical attribute. Missing values, we filled it with median. And then we learned how to convert the categorical values. Categorical values as in like named values, converted it into the 0, 1, 2, 3. Then we converted that into one hot encoding like this, saying we for all the values, if there are 20 values, there'll be 20 columns that will create, and we'll just mark the one which is correct. Okay, so this will become from the text, it will become the numbers. All right, in very simple words. So that's what we did. Then we combined the two approaches, first converting the text into numbers and then converting into a sparse columns. Okay, so that's what we did. And then yeah, then we learned that we could create our own transformations that we can call. Okay, now custom transformation is something which we use. Now today we are going to continue from there. We also learned feature scaling. Feature scaling, the standardization is a better technique uh, instead of min-max scaling. Okay, standardization, as in we subtract from the mean and divide by the standard deviation. So we compute how far are we from the how far are we from the center, how many standard deviation away are we from the center, and that's how we generally rescale. Though there are many other scaling functions that we will study at the time of, say, deep learning. We will study the various kinds of other, like sigmoid functions and other functions which do the feature scaling, and there are logarithmic scalings and so on. But the generally it has been found that the standard deviation based scaling is far more stable. Okay, all right. Question for Bintao. When we call reshape with -1, 1, what happens there was that instead of multi-column and single row, it converts it into single column and multiple rows. If there is a array having n elements, it will basically convert into matrix having n rows and one column. Okay, so that's what that reshape to -1 1 does. All right, now let's move on. That will encounter again, and yeah. Now in a usual project, as we are observing that there are many steps involved, and we might lose the track of it, or we might end up executing them manually again and again. So there is something called pipelines in case of mm, scikit-learn. So, and that's what makes the life easier for us. So we will, let's say we want to build the pipeline for numerical attributes. The steps we'll have to do is, um, we have to handle missing values, right? That's what we have done so far. we have to handle missing values using imputer class. Imputer is a transformer which does the work for us. It first computes the median of all the values and then fills in the missing values with a median. And that median is how we define the strategy in the constructor of imputer. I'll show you just now. And okay, so then we talk about, then after filling in the missing values, then uh, we created a combined transformer. uh, we created a custom transformer for combining attributes. Then we did the feature scaling, right? So combining attributes, as in there was categorical one and then there was numerical attributes. We converted categorical attributes into numerical and then combined the two, right? So imputer worked only on the numerical values, right? Imputer worked only on the numerical values. So we had splitted the data set into uh, two parts. One is only the attributes having the numerical value, and other one as the categorical value. Then the okay, should I just draw for a clear picture? So what we did was we had the data set, right? We had the data set. Okay, data set we had split into two parts. Okay, training and test, correct? So this is what we had done, and this is a standard flow. Okay, standard flow. Then training data, we I'm just doing the imputer. uh, so training data, sorry, here this again what we did was we did something different. Okay, training data we split into two parts. Okay, two parts as in the columns, right? The columns, not the rows. So here rows were split, here the columns were split. So this is numerical columns, right? Numbers, and this is text. Okay, so here what we did was here we got numbers and text, and on the numbers we applied the imputer, right? Okay, non missing values, right? We applied the okay imputer, which basically filled in with okay filled in missing values. Cool. So after that, what we did was here the here not test. This is not test. I'm sorry. This is text. Okay. And in the text or categorical data, you can say categorical data. Okay, categorical data. We first converted into numbers. Okay, numbers. You can call it factorized, right? Then after factorization, what we did was we converted into one hot encoding. And these are something you will notice that when we do other projects, this will be done for almost everything. Okay. And then what we did was we did a you say scaling. All right. And after this, we will combine the two. We will combine the two, and as in combine the two, and we'll get the final data here. And after this, we will apply the algorithms here and then do the rest. Okay. I hope this is good. This is clear to all. All right. Now, the same thing we are trying to do using pipelines. Okay. Now, as you can notice that if a new data set is coming, we will have to apply all of these in certain pipeline, a certain method. Or let's say we realize that, hey, we need to do scaling of final data instead of this data. We'll have to move this down. Correct? We'll have to move this down on both of the data. So basically what you will notice is that there are many steps involved in a typical case, and you might have to move or remove these things for various algorithms. And okay. Yes, and now, yeah, thank you, Ross, for that. So yes, we'll have to do a similar thing for the test data also. We'll have to fill in the value with the using imputer. We might have to scale the values and so on. Okay, we might have to do the same thing with the test data. Okay, we are not touching the test data right now because while we start exploring the data, we might end up looking through the entire test results. Okay, so we are avoiding the snooping bias as much as we can. All right. So yes. So this is just one example of what we have done so far and a picture of what we are doing. These steps we will keep on rearranging or adding as we go ahead. All right. Since if we make this pipeline here, let's say we make this pipeline, this pipeline, we can call it with training data or test data. It is up to us. All right. So that's what that's the value proposition of the that's the value proposition of the pipelines. Okay. So okay. Question from Noor. We had one more step of dense or sparse. Can you please elaborate that one? Okay, so let me just show you here. We had one more step of dense to sparse thing. Yes, so I think we are talking about the feature scaling, right? Here. So we use standardized feature scaling to handle even the dense and sparse one. Basically, after one hot on encoding, the values will be sparse. Okay. So, all right. All right. I think that's what you meant. Great, great. So this is the pipeline, what it does, and you will notice the pipelines in many projects, and this is the kind of objective in the in your data science project or machine learning project. The idea is to come up with a model and the pipeline for the entire project. Okay, great, great. So here what we're doing is we are importing the pipeline class. Then we are also importing the other classes required as for the individual transformations or transformers. So here we are saying that pipeline, here is the pipeline, it's an array of tuples. It's an array of tuples. In each tuple, the first one, in each tuple, the first one is the name that we are giving to it, and the second one is the object of estimator. And how do you create the object? By calling that class method with brackets and specifying the initial values. So we are saying we're calling the constructor of this class, and here it will result in the object. And here is this is the name that we're giving to it. Okay. So yes, so what you see is basically this is the this is the sequence of various transformations. Okay. So here first we'll call imputer, then we'll call combined attribute adder. This is the one which we created yesterday, and then we will call standard scalar. And of course, we have forgotten to import imputer. A question from Gopi: can this imputation method of using the median strategy through the imputer be used in other dataset? Yes. I see. I see. So, okay. So which data set are you trying on Kaggle, Gopi? Yes, that's right, Noor. So each of these estimators can have a method called fit and can have a method called transform. Fit basically learn from the data, and transform basically fills in the data, right? All of all these classes would have those two methods. Remember, yesterday we defined this. So combine attribute adder has two methods, one fit and other adder, one fit and other transform. So in case of imputer, let's take a look at the imputer. What would happen is when we call this pipeline with fit transform, it's going to call first fit, right? When we are passing this housing num is going to first go to the imputer, and at imputer is going to call fit underscore transform, meaning first it will call fit, then transform. What does it mean? It will first find out the median of all the columns in the dataset. It will find the median of all the columns, or you can say median of all the attributes in the dataset, and then it will substitute the null values with the median, right, as part of transform. Fit means finding the median, transform means filling the empty values with median. Okay, in case of imputer. In case of combined attribute adder, we did not have anything inside the fit, but we had the method inside, something inside transform. Okay. And then the standard scalar, what does it do? It basically computes the standard scalar. Also has a similar way that it will first fit and then transform. First it will find the mean and standard deviation, and then it will compute the in the values. Okay, it will compute the it will apply that formula on all the values to normalize the values. Okay. All right. So we use pipeline so that we can sequentially apply many transformations on our data. Does that make sense, Binta? Yes, pipeline itself is a class, and so to pipeline we are passing an array of tuples, okay, or people call it tuples. So it's an array of tuples in the in and each of the tuple is nothing but contains a name and the object of our individual transformer. All right. So okay, a question from Gopinath. So if I want to impute only one value in a column instead of all values in a column, how do I do that? Okay, a good question, a good question. So what we'll have to do is probably in the imputer class, we might have to specify an argument saying only apply imputer on this. Or instead of passing the whole data set, we will just pass the one of the columns. Okay, we'll just pass one of the column. Yes, this housing, the numerical values is what we are applying. This is the pipeline for numerical values. Okay. So, again, the transformers have two methods, fit and transform, right? Fit basically does not return anything, while transform returns the next data set. Okay. So it is important to know that the last one must have, last estimator must have transformers. Last estimator, it is actually called estimator. They call it estimator. Um, okay. The last must have the transform method because it has to return something at the end of it. So when we are calling pipelines fit method, it is going to call fit underscore transform method or fit followed by transform method, uh, because fit underscore transform is equal to calling fit and then transform. Okay, it's going to fit and transform on all of the transformers, uh, and passing the output of each call as the parameter to the next transformer until it reaches the last one. For the final estimator, it just calls the fit method. Okay. All right. So that's what it does. And pipeline at the end of it is kind of represented by the last method. So if we are calling fit on the pipeline, it's going to call fit and transform on all of the estimators except for the last one, on which it's going to call only the fit method. Okay, let me go back here. If we are calling fit only fit instead of fit transform, if we are calling fit on this, it'll going to call fit and transform here, fit and transform here, fit and transform, but on the last one it's going to only call fit. Okay, so that's the way it works. And now, please note that the scikit-learn does not handle data frames as we talked about earlier. Scikit-learn mostly operates on NumPy arrays. So we'll have to convert our data frames whenever needed into the NumPy array. Okay, so how to select the columns from the pipeline? Let's create a data frame selector to select the numerical or categorical columns. Okay, so this part that we talked here to split it here, we are going to use a selector here. The selector will kind of do the splitting for us, and a question from Tanmay is, fit transform is scikit-learn feature. You can say that. Basically, fit transform is a method of pipeline, as well as it's a method of each of the estimators. Okay, so most of whether you are designing a pipeline or designing your own estimators, your estimators are supposed to have fit and transform method. Okay, fit and transform method, and this fit transform is inherited from the base class, which means fit transform comes for free to you. And whenever we are calling fit transform on any estimator, it's calling a method called fit that we defined and transform that we defined. So here we are talking about two kinds of estimators. Estimator is something that gets executed as part of the pipeline. Okay, so estimator could be custom, or estimator could be custom, or um, estimator could be our own. Sorry, estimator could be out of the box from the scikit-learn, or they could be custom. Okay, so what we have is we have data frame selector. This is the class that we are going to do. What data frame selector is going to do is whatever columns that we give, it's going to pick only those parts of the column. Okay, so it'll select. So here is a very simple, very simple estimator. It's called data frame selector. Okay, what it does is we need, whenever if we are creating our own estimator, if we are creating our own estimator, we have to inherit from the base estimator and transformer mixin. Okay, okay. We have to define its constructor. This is how we define constructor, and we pass the self, and this is the extra argument we are saying. Here, since we are saying that we will pick and choose only those columns and convert that into a NumPy array, which we are passing as the argument to the constructor. So it has three things: constructor, fit, and transform. Fit does nothing much, and transform basically transforms transform X into something. Transform basically is selecting those attributes. So it's saying self.attribute names, which is this, and that's all. So as part of constructor, whatever arguments are passed as the to the constructor, those will be set to the instance variable, okay, so that we can use it later. So when we initialize this, we will be telling it that these are your columns, okay? And when we call the transform or the pipeline, either we will call the transform or the pipeline will call the transform. And at that point of time, this will be done, okay? Here what's happening is we are saying data frame and give me these columns, and then we are saying dot values, meaning give us the NumPy array. Okay, this will basically do two things: one, selecting the columns; other, selecting the column, and other selecting the converting it into NumPy array. Noor's understanding is estimator is a step in pipeline. That's right. It's like a workflow. So workflow is a pipeline, and step in a workflow is estimator. That's correct. Okay. Attribute names in NumPy array. Yes. Attribute name in the data frame. Okay. So self.attribute names, basically X is the data frame. Okay. X is the data frame, and it's going to accept these attributes. And when we call data frame like this, it basically picks up only those columns, and dot values convert that into a NumPy array. Okay. Okay. A question from Gopi. Why is the default argument in the fit function in the class data frame selector? Are we not fitting with respect to both X and Y axis? Why is the default argument in the fit function in the class data frame selector? Okay. Okay. Yeah. So here what we're doing is we are ignoring this argument. Okay. We are ignoring this argument. And yeah. Okay. Okay. So in the pipeline, we're going to get X, we are going to get Y. Y, the default value is none. And we are anyway ignoring it. We are not using it anywhere. Let me see how it goes ahead. Okay. I see. So thank you, Ross, for this. Basically, there is a module that probably works well with Scikit-learn and Pandas. Probably that would also be doing a similar thing, because Scikit-learn, the way it's designed for performance, and the NumPy is kind of also designed for performance. So probably the scikit-learn pandas would be converting most of the functions internally into NumPy array. That's my guess. Okay, I'll have to take a look at it. But thank you for it. Now, so now let's use this. Let's use this estimator. And how do we use this? By putting it in front here, right? That's what is happening at this point. At this point, we basically um, doing calling this right in the beginning. So we are saying here is our numerical attributes. Okay, here is our numerical attributes. And here is the list of our numerical attributes, and that's what we are giving to data frame selector. And this is going to be executed in the beginning. So when fit transform is called on our fit transform is called on this, it's going to call fit and then transform. So this is what is going to happen. It's going to whatever, if we are calling this pipeline with housing data, it will it'll first pick the numerical attributes, then apply imputer, then convert it into categorical attributes in, sorry, a combine attribute adder, as in, let me show you what it means by combine attribute adder. Combined attribute adder, the feature scaling, essentially the feature scaling, I think that's what is combined attribute adder. No, let me just go back. Yeah, I think this is what we were doing. Yeah, this is the one. Okay, so this is where we defined our combine attribute adder. What it does is it takes this. Oh, this one basically was adding that one we skipped in the diagram. That one we skipped in the diagram. So here in the numerical side, before scaling, we did some more things. Okay, we did some more things here. That one we missed. Okay, that one we missed. And let me just put it here. We call it new. We created new attributes, right? We created new attributes somewhere here. Okay, so yes. All right, so I think, yeah, there have been just so many steps, so we kind of keep on forgetting. All right, so after we have selected the columns, we are calling imputer, then we are calling this one, the one where we are creating the bedrooms per room, and then we are saying we are scaling things, scaling all the values, and at the other side we are selecting only the categorical attributes, which is ocean proximity, and ocean proximity will be converted into categorical attributes using categorical encoder. Okay, and here we're basically converting it into one hot encoding. Okay, that's what we are doing here. So we are basically using an out-of-the-box categorical encoder, which is going to convert our data into one hot encoding. Okay, so that's the one. Now we got two pipelines. We got two pipelines. One is this side, one is this side, and other is this side, right? We got two pipelines, and the way we do is by using the feature union. Okay, so we are saying that here are our pipelines, num pipeline and categorical pipeline, and we are combining them. So when we are calling the main data with the full pipeline, first it is going to be called, then it's going to be called. Okay. All right. So both of the pipeline start with the selector transformer. It simply transforms the data by selecting the desired attributes and while drops the rest, right? So both of them are going to call here, both of them are going to call the same class but different attributes and so on. All right. So at the end of it, the full pipeline the full pipeline dot fit transform is going to do the entire flow for us. All right. Let me just go back and try to run it. All right, so this is where we are, and let me run everything till here. Okay. Looks like yes. Thank you, Ross. Let me take a look at it. Okay. All right. Let me also. Okay. Let me clear all the outputs. Okay. I've just cleared the output and try running everything. Yeah. It is still running. Okay. No worries. Looks like I can just let's say kernel restart. Okay, kernel restart, connected. Now I'm saying run all above. Okay, no worries. So, all right. Good. So basically, this is what we did, and yes. So what we have is this one. So we define two pipelines, correct? Everybody's okay with these. We could define two pipelines. Selector, select the columns, then substitute missing value with median, then combine attribute adder, as in you remember what we did, the new step, Noor, the one where we were trying to figure out the new attributes which could impact, right? So one of the attributes we created was rooms per household, and other was the other was the um, one was rooms per household, and what was the other one? Other one was rooms, bedrooms per room, right? Those were the other attributes that we created. This combined attribute adder is that one. Okay. Then standard scalar, then again for the second pipeline, right? So we run this, and then we combine the two pipelines, and finally we call this on our housing data set. All right. Then we call this on housing data set. So this is our data set that we have prepared. A question from Gopinath: is there a limit to the number of pipelines you can have? I don't think there is a limit to pipelines. As long as it's fitting in the memory, it should be possible. And the memory taken by individual pipeline will be really small. Okay. So, all right. So the outcome of this one, the housing prepared, is this. Okay. A question is, can I take a look at the individual num pipeline? Okay. So if you want to just run the individual one by yourself, so what you can do is you can do the same thing like this. Okay. So you could try saying num pipeline and doing this. Okay, so the interesting part is the way we are calling the individual pipeline like fit transform. In the same way, final pipeline can also be called, and all of these methods, all of these estimators, we can call it in the same way. Okay, all right. Question from Gopinath: how do I interpret the output from cell 73? Okay, the cell 73. Yes, interesting question. So yes, it's a little difficult to interpret. A better way would be to just take a look at, say, housing, and we say head. Okay, and here we have these values. So okay, housing prepared, and we are saying housing 0. So this does not have y, it has only x. Okay, I'll talk about x and y soon. So let's say 0th record is this. All right. So each of these values are corresponding to, so this one is longitude, this one is latitude, this one is probably the housing median age, and so on. All right. Good. So what we have is now we have housing prepared. Housing prepared contains the final result of our data cleaning and other preparation involved. Okay. So prepare data had basically the output of our work at prepare data is this. Okay. This pipeline, this full pipeline, and the this numpy array is the outcome of all execution of our final pipeline. Okay, so now let's start with the actual work, which is selecting and training a model. All right, is everybody comfortable with it so far? So this is what we call creating data pipelines when it comes to machine learning. A question from Noor: how do I verify that pipeline has worked fine? Okay, good question. Mostly the pipelines work. Okay, if you want to ensure that what happened in case of pipeline, right? So I think what you can do is you can actually execute individual items by yourself, and then you will know whether it is working or not. You can check the outcome of individual item and then see it is working or not. All right. All right. So it doesn't display the individual activity. What you can do is you can actually access the, I think you can access the constructor of the, okay. So this is the pipeline. So we can say steps, and this is this first step. Okay. And it is showing us that steps was called with these values, right? So you get a basic idea about it. Okay. So step one was called with these arguments and so on, right? And the second step was this and so on. I just want to see if this one really works. Okay. All right. This is another way you can do it. Okay. So this is another way you can probably call it. All right, so it says, okay, I think I got it. Okay, so basically you can call the individual steps in this way. Okay, you can call the individual steps. So I'm calling the selector here for this from the num pipeline and so on. Okay, so yes. All right, you could always check all the steps using the steps method on the pipeline object. Okay, so I just demonstrated. Okay, all right, yeah, that's what I was showing you. Thank you, Kamal. So you can see that this one, this value is this one after scaling. This value is latitude after scaling, and this value is housing median age after scaling, and so on, right? And yes, in the last one that you see, ocean proximity, here this one represents the first one, 1, and rest are zeros, right? Correct? Now let me show you the second record. All right. What is second record here? The last one is, I think the orders are different. No, not second record. I'll just do 1 instead of 0. Okay. So yes, 1 is also this. And if I go to the 2, you can take a look at it. The last one is 1. You see that? Last one is 1, which is this. Okay. And all right. So probably what I can do is I can do this. I think this is easier. Yeah. The other easier way would be that we create a data frame with the same housing header, same housing labels and the column names, and then it'll be very clear. Okay, so you can see that. Okay. All right. I think we can use this tab name. You're right, Ross. So with the tab names, we could do that. All right. So you can basically look at it. The other question that Kamal is asking is, why do we need to scale everything, right? So it's generally safer to be on this side, as in on the scaling side. It's safer to have scaled data, right? Because it's not going to do you any harm, right? You at the end of the day need the output, right? And whatever is the okay, I think yeah, for most of the algorithm, it'll make sense to actually scale the data. Otherwise, you always end up with the extremes or not. I mean, uh, the values overflowing. Okay. So yes. So see, there will be some extra columns, right? Because of hot encoding, right? These are those columns here in the last one. All right. Now let's move ahead. Did I miss any questions? All right. Let's move ahead. Great. Uh, yes. So do you mean the pipeline will use, okay. In case the values are scaled, will use less memory? Maybe, but um, maybe, but because the data type is same, the values are going to be on the similar line. No, actually, we are scaling all of the attributes. Okay. So in the standard scaler, if you notice that we are in the pipeline, right? Here, if you take a look at our pipeline, so here the scaling is happening on the numerical attributes only. Okay, all of them. Great, wonderful, wonderful to have yeah, reached here. Now let's take a look at quickly what we have done so far. Frame the problem, got the data, explored it visually, and understood various aspects of it. Learned how to create the training and test data. Then we learned the transformation pipelines in cleaning up, preparing. Now we are ready to train our model. Okay, so now is the time that we are going to train our model with something called linear regression. The goal of this step is to train 2 to 5 models and select the best one. Let's understand the overfitting and underfitting before training a model. Okay, these are the terms which we are going to use again and again. Say if you are visiting a foreign country and the taxi driver rips you off, you might be tempted to say all taxi drivers in that country are thieves. And this is overgeneralization. So this is overfitting. Okay, this is overfitting. All right. So, all right, this is called overfitting. This is called overfitting. So basically, um, this is what we also call overgeneralizing, right? This is very common in case of our daily life, that we overgeneralize a lot of things. Okay, so okay, so yeah, this one we had added recently and may not be in the one that has been shared. So let me just uh, update the slides after this session. Okay, if they're not updating, and yes, Abhinav would be taking a look at it, right? So good, great. Now, so machines could also kind of fall into the trap of overgeneralization like us, and this is basically this is very common with a lot of models, right? So though model might look as if it's performing great on the smaller data, and the moment we go for unknown data that we have not seen it, it may not work well. Okay, so overfitting occurs when machine learning algorithm captures unnecessary noise, and intuitively overfitting occurs when the model or the algorithm fits data too well. Okay, and overfitting is often a result of an excessively complicated model. Okay, excessively complicated model. All right, let's consider an example of overfitting. Okay, here a high degree of polynomial strongly fits the housing prices, right? If you, let's say the data looked like this. So you quickly, generalized it to draw a curve like this, right? And looks like it's perfectly fitting. But the moment, let's say housing sizes started increasing, you saw that, okay, so let me rephrase the question. Imagine that we were computing the prices of house based on house size, okay, and we looked at this small data, and looking at this data we realized that, okay, it doesn't fit the linear regression, but it looks like it would fit the curve. Okay, so we fit a curve here, we fit a polynomial. Now now let's say we look at more data, and we end up fitting the polynomial in this way, right? We fit the polynomial in this way. This is basically overfitting the data. Ideally, there could have been a single line that could be going like this. A linear regression will fit better. A line will fit better than this complicated curve. So this is basically an example of the overfitting. All right. Now there is something called underfitting the data. A complex model may detect patterns like the fact that all countries in the training data with a W in their name have a life satisfaction greater than 7. Okay, so one is overgeneralization and other is undergeneralization. So sorry, we will talk about the other underfitting later. So another example could be of overfitting is here, that let's say we looked at all the countries and we did not look at all of the countries. We missed out a couple of countries. Okay, and we tried to figure out the relationship of the name with how rich they are. So we looked at the names and we found that the frequency of W seems to be there. As in, if the name of the country contains W, they are rich, right? So this is another example of overfitting. So because we missed Rwanda and Zimbabwe, right? If this was right, then what about Rwanda and Zimbabwe? They don't have, they're not rich countries. Okay, so basically when we miss out on critical parts in the data, we might end up overfitting or overgeneralization. And this is very common in case of data, in case of machine learning, and that's why we were trying all kinds of things. we were we were we did the stratified sampling exactly for this kind of cases, that we might miss out some of the data, and we end up only looking at parts of the data. We start overgeneralizing. So that's why we need to be aware of overfitting. Okay, and there is regularization can be one way in which we can tackle the problem of overfitting. In overfitting, we we ba- we put the constraint to make the model, put constraint on the model to make it simpler. Okay, the amount of regularization to apply during learning can be controlled by hyperparameter. Okay, so we'll talk about this. For example, if our model depends on n parameters, we can put a constraint on k of the parameters, so that in case we have to only adjust n minus k parameters. So okay, let me go back. What does it mean? So Let me see if I have a diagram. Yeah. Okay. So regularization is a technique with which we will be able to handle the overfitting, right? Regularization can be, all right. Okay. So one way is that we do the regularization. Regularization means we put the constraints on our data and we put the constraint on the model to keep it simple. Okay. And yes, so that we don't over generalize in case of too much of data. Consider, okay. Let's say, yeah, I think this is a better example. All right. Okay. I'll explain what it means. Going back to here. All right. So we have two choices. One is that when we are when we have some data, we have two choices. Number one, we miss out on some of the data, and number two, we we use a simpler or a complex model, right? So we generally use the simpler model, but do not miss out on various points. Imagine that. I think this example is far better. So consider a linear model. Let's say we have a linear model, as in we are trying to draw a line. It has got two parameters, slope and the distance from the center. Slope and distance from the center, we can vary both the things, okay? And it gives basically 2 degrees of freedom, right? We can tweak the height, we can tweak the slope, correct? And if we forced that the if we force that the height, the theta one, that is slope of the line is fixed, the algorithm would only have 1 degree of freedom, right? If we allow the algorithm to only modify theta 1, okay, it will produce a simpler model than the 2 degrees of freedom, but it will be more complex with just it will be more complex than with just 1 degree of freedom. Okay. All right. So, right. So the dotted line represents the original model here. Okay. So you see that there were few countries missing here, and there was a dotted line here. And the dashed line is our second model trained with all countries, this dashed line, okay? And the solid line that you see here is the linear model trained with same data as the first model, but with regularization constraint, okay? So, yes. Okay, let me go back. I think there are few things that we need to go with. Okay, so all right. All right. Uh, for some reason, it just crashed. Are you able to hear me, everyone? All right. Okay, I think I missed on a lot of questions. Can somebody just paste all the questions that have been posted? The Zoom had just crashed. All right. Okay, let me take questions one at a time, then we will talk about it. Okay, so here is the first question. All right, could you post your comments? I actually missed out the entire comment section. Shahrukh, you were saying something. I think that's the point. I missed out everything. So after your chat, can you post everything along with your chat? Sorry about it. All right. So yes, is it open for you or how's it? Okay. Can you just copy paste the entire thing after your last messages? I kind of missed since last maybe 5-6 minutes. Okay. All right. So let me see if I can. All right. Good. Good. So let me just copy paste it, whatever I've learned. All right. So a point from Saruk was, it is basically putting constraints on the parameters that make up our model. That's correct. That's correct. And point from Ross is it an art to get this figured out along with avoiding over and under training? Um, though it's an art, but I mean, you can figure it out. We will learn it together, as in the over how to tactically or how to strategically avoid over and under training. Okay, so a question from Gopi was that, firstly, how do we measure overfitting? Good question. How do we measure overfitting is when our model is not generalizing well. Okay, generalizing well when we run it in with our test data or data we have not seen, and it's giving us um, bad results in the cases where um, in the cases where it has not seen a similar data before. Okay, that generally means that our model is not performing well. Okay, so is there a better method than using R squared coefficient? R squared coefficient does a very good job of detecting overfitting. You know how? Because in case we are wrong, it will basically square it, meaning it will amplify the if our overgeneralization is far away from some of the data points, far away from the sum of the data points because it has fit the wrong thing, then the R squared actually amplifies the distance, right? When we square something, it is far more bigger. So 1's square is just 1, while 2's square is 4, and 3's square is 9. So it basically amplifies the mistakes in the model. Okay. Next question from Gopi was, how do we know which parameters to constrain? Finally, what is meant by degree of freedom? We'll discuss it. All right, we'll discuss it. Okay. Second question from Bintao is, what does it mean by regularized here? Regularized means that we are going to control the number of parameters that we are going to vary. All right. All right. So, all right. I think this is something that we have done. Okay. Did I miss any other question? All right. Great. All right. So R squared coefficient, okay, a question from Noor is, what is R squared coefficient? Basically, you remember what we were doing is we were having we were trying to fit the, let me open, okay, you remember this? So what we were doing is, right, we had put the points here like this, right? And when we draw a line that is fitting our model, this is the distance, right, from the actual values, each of the, so the, so this is our hypothesis that this is how our data, this is how our model is, and these are the actual points. The cross ones are the actual points. So this distance from actual y is the thing that we are trying to predict. Okay, so we are predicting for this value of x, this value of input, we are predicting this output, right? We are predicting this output, while the actual output was this. So this is the distance from the, this is the distance from, this is the distance from the, these are the three distances from our predicted value, right? So what we do is we take these distances and we square it. Okay, so if it is, let's say, A, B, and C, the result is going to be A square plus B square plus C square. Okay, uh, and we square root it and all that, right? So if we had just done like A mod, right? Mod also will remove the negative sign, right? A mod plus B mod and C mod, then it'll be here the bigger errors are not being emphasized. Okay, that's why a squared error is generally a choice. Okay. A question from Gopinath: is there a threshold for R squared coefficient to decide overfitting? There's not a threshold as such, but if our model is not performing well, as in the outcome that we are getting is um, far away, as in more than one standard deviation away, uh, or is not less than one standard deviation, then we generally call that model is not at all fitting. Okay, so All right. Okay. So let's take a break. And also, I think a better idea would be to skip the overfitting, underfitting. I think when I start talking about the results of the learning, okay, when we talk about the results of the learning, then we will come back to overfitting and underfitting. Then all of this will make more sense to you. Okay. So I think we can discuss overfitting and underfitting at later point of time when we are done with the results, right? So yeah, thank you, Abhinav, for that input. So I think, yes, it makes sense to me because what's happening is right now that I'm worried about that you did not get these many things, and that's why I'm kind of worried that, okay, let me first explain the model. So I think we should start with the training model just after the break, okay? And then go back to fixing the our if our model is doing the underfitting or overfitting, we will try to explain it then and there. Okay, so we'll learn those parts as part of after this. All right, so great. Let's have a quick break. Okay, so let me. All right, do you mean this diagram, Gopinath? All right, I'll share that. Okay. So is it possible to share right away? Oh no. Okay. So let me just save it somewhere, then it'll be easier. Okay. So easier. All right. All right, great. All right, so let's start. All right, so where are we? We are somewhere here, correct? Okay. Okay, so here we are importing linear regression because linear regression is what we're going to use. And then we're instantiating linear regression, and then we're calling fit. Okay, fit means learn from our model and prepare, learn from our data and prepare the model. Okay, so we are passing two things. One is the training set, okay, and the target column. Target column as in the house median value, right? The value of the house. These are the input parameters. This is the output parameter. Okay, these are various columns except for the output, and this one is the output one. All right. Please notice that here we are passing housing prepared. This one does not have our target column. Okay. Housing labels is the target column, which is we call it small y, and this is called capital X. Okay. So all right. So let's do this. So it's going to take a bit of time. Now it has done that. It has uh, basically fit the data and the model has been generated. Okay. All right. Okay. Now let's try the full pipeline on few training instances. Okay. Let me go back here. Right. So here, basically, here we are saying that let's just pick few 5 records from it. First five records from both the data, both the sets, and then we use the full pipeline to transform that. Okay, full pipeline to transform that and do the prediction. Okay, do the prediction. So I hope you got the idea that whenever we want to predict some value, we will have to pass that data through our pipeline, right? So let's say we want to predict the first 5 values, okay? So what we do is there was the housing data set, right? The initial one. Out of that, we are going to just pick up first 5 rows, and this is the data of the actual one, the actual, as in the input parameters, and this is the output. What was the output? Output was the housing median value, or we call it target sometime. Okay. Now, here we are saying that run run the full pipeline, meaning let's clean up the data. Let's do normalization, sorry, standardization and everything using the full pipeline. Okay. So once we have the final data, then we can use this model, linear regression model that we generated to predict the values. Okay, to predict the values. All right, so let's take a look. So you can see that the values predicted by this are these. Okay, let's take a look at the actual ones. The actual was this much, and we predicted this much. Okay, the actual median houses price was this much, and the predicted is this much. Okay, now let's try to compare the predictions and the actual ones. Okay, so what we do is we are going to say housing label. All right, so these are the predictions. Okay, so let's just try to compare the two. We are saying housing predictions equals linear regression dot predict, and then here we are doing it for these records. Okay, let me just see. Okay, we are actually doing it for the entire data set. Okay, so what we are doing is from the data set that we learned, we are predicting the values for the same and comparing with the original. So this was the original. These are the predicted. Now, whatever we did here for first 5 records, we are doing it for the same entire data set from which we we um, we prepared. Okay, so this is what we did. All right, so here we have housing prepared. This is the original data on which we trained the data set. We also did the predictions on basis of this, just this is just for testing. And here, this is what we got. Okay, this is the root mean square error. So on these kind of values, the results, this is the root mean square error that we are getting. It's not that bad, but it's not very great also. But okay, so yeah, so on a value of say to 286,000, we are getting an error of 68,000. Okay, so we are this much off from these values on an average. All right, so this basically gave us some results, but it's not very good. Yeah, it's not very good. So we'll try some more models and see if we can fit other models to get better results. All right. A question from Tanma is, what is the range to conclude RMS error is okay? So RMS error, you should always compare with the actual values and see that how far are we, okay? Overall, this is the range of values, and our RMS value looks kind of in the similar, kind of, it looks, how much is it? 6 into 4. It's like 25% of the actual value. So you can say that we are kind of 25% off from the actual value. Okay, that's how we generally perceive the perceive the root mean square error. I hope everybody is okay with this. All right. 25% looks big. Yes, it's big actually. So if you take a look at, yes, our goal is to minimize this error. Okay. And if you take a look at the actual versus predicted here, actual versus predicted, we are basically seeing that for some of the records, it is as big as 26%. For some, it is as low as 6.7%, right? So the RMS value is an overall indicator of the error, okay? And we will compare the RMS values amongst the algorithms, okay? Yes. So basically, this is the result of the linear regression. All right. So the predictions are not exactly accurate. The fourth prediction was far off by more than 27%, right? And using this, we computed using RMS value, we computed the overall root mean square error, which is basically 68,000, right? This is not clearly very great RMS value, okay? And on a value of between 120,000 to 265,000, that the predicted error is around 68,000, okay? Which is kind of more than 25%. All right. So this is basically an example of the data underfitting. Underfitting as in our model needs to be a little bit more evolved in order to fit the in order to fit uh, in order to give the output better. All right. So kind of maybe we are trying to put the linear regression instead of the maybe some curve or some other more evolved algorithm. So so we can try other powerful models. Okay, question from Noor. Question from Noor is, if we can draw both, then we can have a better idea where predictions line is heading. Underfitting cause percentage is negative, right? Mm, so it's not that it's percentage. It's not because percentage is negative. It's because we are off from the predictions. Okay, so underfitting means we are getting a lot of error, meaning our model is not really good fit for this kind of data. Okay, that's underfitting. In overfitting, we generally get better accuracy over certain data set, and for certain data set, the accuracy generally jumps really big. So here, it's a case where our model, see, because we have trained it on the entire data, and our model on the data it has been trained itself is not giving a good result. In case of overfitting, the data on which the model has been trained, it gives you very good results, right? So therefore, here it's a case of underfitting the training data. All right, we'll come back to these parts. So maybe we would need to go to a more powerful model. All right. A question from Gopinath. So if we use population to train the model, it has already been exposed to test portion. Yes. So We are testing on the same data on which it was trained. Had it been a case of overgeneralization, this is where the overgeneralization works well. Overgeneralization is that um, all the countries having name as W are doing good. Okay, are rich, right? That's overgeneralization, meaning we have seen a smaller set of data and our model, our theory is fitting very well in this. Okay, so at least the had the model been fitting on the same data set has been giving really good results, then we could have said that, okay, this looks like a case of overgeneralization, but here it's the opposite. Okay, here it's the opposite. Here on the same training data on which we have trained it, it is giving us decent amount of errors, right? All right, so let's train another algorithm. Let's train with another regressor algorithm called decision tree regressor. We will go into what decision tree does as we in the another chapter, but let's think of it as just another black box which is going to predict the values. Okay, for time being we can assume it to be a black box. Okay, so what we are doing supervised regression, and another algorithm other than linear regression, we have decision tree, correct? So it's capable of finding complex non-linear relationships in data. We will discover that in the later. All right, so we are importing decision tree regressor, and here we are defining an object of it. And again, please notice that almost all algorithms have the same mechanism. Okay, fit and fit, transform, or fit and predict. All right, so we are feeding the same housing prepared, and then the housing label. This is called capital X. This is called capital Y, and then we are predicting in the same way. Yeah, let's just go back and try that. Now we are importing the decision tree regressor. We've just created the instance of it. Here, please notice that again, decision tree regressor, we are passing the random state. Okay, we are passing the random state. So these things, right? Here we are saying that start with this state. These are kind of knobs. These are kind of preferences that we are setting to these algorithms, right? These are also called hyperparameters. These are called hyperparameters. What was parameter? Parameters are the columns of our data set. Parameters in our case are the columns of our data set, such as latitude, longitude, and the population and so on, right? And here this parameter to the algorithm is called hyperparameter. Okay, so we are just defining some random state. Okay, because decision tree internally needs to do the random number generation. Therefore, we are passing a random state so that every time this gives us same result. We'll talk about later why this, why not something else, when we will learn about something called hyperparameter optimization. All right. So yes, I think it should run without this parameter as well. Okay. In that case, it will basically generate random. Now we can try that actually. Let's see. It should run. Yeah, it's fine. Okay. Now coming back to it, so we have generated a newer model with decision tree regression, and here let's try to predict the values, the housing predictions, and then using the mean squared function, we are comparing the overall value. Now this is amazing. You see that? This is amazing. This is giving a root mean square value of 0. Okay. We trained it on the same data and we tested it on same data. This looks like a case of overfitting. Yes. Okay. All right. this is something looks like really good, but there is something strange here. There is something strange here. Okay. And this is an example of overfitting the training data. All right. Let's evaluate the. Now, in such cases, wherever you encounter this, instead of taking this to our second part, right? We have kept the testing data separate. Instead of right away running this algorithm against the testing data that we had done earlier, we're going to use something called cross-validation technique. Okay, we're going to use a cross-validation techniques, and in cross-validation technique, okay, so till the point we are exploring our algorithms, we want to be on the safer side. We'll touch the testing data later, right? Because we don't want to overfit our model at this point of time. What if we overfitted our model on actual test data? Okay, so until we are confident of our model, we will do the cross validation. How do we do that cross validation? Let's take a look. Okay, in cross validation we use part of the training set for training, and and so what we'll do is same training set what we have used so far. What we'll do is we will sample it. Okay, so whatever we did with bigger data set, right? So I'll show you this. Okay, so we had a bigger data set, right? And out of this, we cut it into two parts. Okay, like this was 80% and this was 20%, correct? And out of this, we are going to do what we are going to do as part of cross validation. We will train 90% on it, and we'll test on 10% on it. Okay, and this we are going to do. What we're going to do is we'll break it down into say 10 parts. We call them folds. We're going to break it down into 10 parts. Pick one part, use that as testing, while use the rest as training. Okay, so this is what we are going to do. This is what we have done here in the diagram. We had original data set, we broke it down into training and test, and before we finalize the algorithm, we want to stay with training data set, right? And further what we've done is we are dividing training set into two parts, a smaller training set and a smaller validation set. And this is for training the model and evaluating the model. And this is how we'll compare the model. The way we do is, what we do is we randomly say break it down into folds. We call it folds. Okay. In the first iteration, we might pick the last one as the test fold. In the second iteration, we will use the second last for testing, and while rest remaining parts as the for training. So we learn on this whiter part, right? What color is this? I mean, I think it's slightly pinkish. All right, so we train on this part and test on this. Then in the second iteration we train on this and this and this, right? And we test on this. So this is what we're going to do 10 times. If we are having 10 folds, we'll do it 10 times. If we are having 20 folds, we'll do it 20 times, and so on. And then we will compute the error in both the cases, in all the cases, and then we'll sum up. We'll sum up. Yes, I'm colorblind, so okay. And statistically, 10% of all males are colorblind. Okay. So the chances are that in the class there are at least there may be two colorblind people. Okay, more than one. Okay, yes, I'm amongst the training set. All right. Okay, good. Uh, so, so you can see that we basically break it down. We break it down into folds, and then we test it. So this is called cross validation. All right. So a question is how many folds we generally have. We generally go with, say, so if our data is not big enough, then it may not make sense to go for, yeah, right. Let me, yeah. Question is how many folds we generally go with. The more folds, the better. Okay, but but it will take a longer time, right? Because if let's say here, the training has to be done from the beginning 10 times. Okay, so the 10 folds are something that we consider okay, all right? Because if you go for say 50 folds, it might take a longer time, okay? And the result may not be too different, all right? So because so what we do is basically fold is nothing but breaking the data into parts, and fold is nothing but, so here we are breaking our data into 10 parts. We're picking the last part for testing while we are keeping the 90% of the records for training. For on this part, we're going to train, and this part we're going to test. All right. Okay, so here. I hope that gives you clarity. So we are going to use train test split function to split that we have already used. And okay, and training set into smaller training set and validation set, and train more into smaller. Okay, so what we're going to do is, as part of this, internally, either we write our own algorithm, either we write our own algorithm to do this. We can write like a loop, or a loop in which we are breaking data into 10 random parts, and then mm, loop over these parts and use the remaining 10 into use 90% of the data for training and testing, and then keep the error and do that. And that's what the cross validation uh, method of cross validation method of our cross validation method of our scikit-learn does. Okay, so cross validation score. Okay, here we are initializing cross val score. Okay, we are telling which algorithm to use, right? Because it has to run this algorithm those 10 number of times. We are telling this is the algorithm name, this is the input data, input parameters, this is the output parameters. Okay, and these are target variables, we call them target variables, target parameters also. And the scoring, as in the what kind of scoring do we require as the output. So here we are saying negative mean squared error. Don't mind the negative, because they the way they ended up is they started recently they changed from mean to negative, because I'll tell you the reason. Okay, as part of scikit-learn, they earlier it used to be mean squared error. They shifted to negative because the error has to be minimized. Therefore, the scoring here was the scoring has to be negative of the error, right? So while score means something good, an error means something bad, right? Therefore, it's better to use the negative mean square. So it's basically a terminology difference. The result of it is going to be the negative of negative mean squared value. Okay. And here we are passing the number of folds. That's what we are doing. And let me go back and run it. So we want to use the root square, root mean at the end of it. We want the result to be the mean squared error of all. Okay, let me show you again what we are trying to compute. We are basically computing the summation of all RMS errors. So we'll do the error here. And how do we compute error? Sum of squares of differences from the between the actual and expected. Okay, so we diff the actual and expected values in this, right? So this test part is, what does it mean? We'll have these values, we will have the predicted values of the same data set, and we will diff the two, square the differences, sum the differences, and that will become error. And then and this is divided by, I think, divide by n also, number of records. Then what we'll do is we'll sum up all the errors and divide by number of folds. We'll sum up all the errors and divide by number of folds. Okay, so that's what we are trying to do. So as a result of this, we'll get scores which is negative of the total error. We'll get negative of total error. Therefore, the root mean square, as in the square root, is going to be this one. So here it is the mean squared error, not the root, mean squared error, and here we are computing the square root. Okay, so it is not taking the test data set, by the way. Okay, so let me go back what it means. Good question. So question from Binta is, why does cross-validation need a test data set if it is doing on the whole data set? So it's doing, you remember we broke down our data into 80-20. So what we have done is, this one we have hidden. With this, we don't want to look at it right now unless we have finalized the algorithm. Once we have finalized the algorithm and everything looks great, then we will go with this 20%, right? Go with this 20%. Now, on this 80%, right? On this 80%, we are breaking it down further into 10 parts and then picking the test data set, that 10%, and then doing that. And we are not doing it. This cross validation function is doing that. Cross val score is doing that for us. Okay, that 20% is just, we are keeping it away. We will do it later. We will test it later. Did I make sense, Binta? Okay. Now, earlier we got the root mean square error at 0, which is very, very strange. And so what we're going to do is we're going to use the cross validation score. Okay. A question from Gopi. I'm getting name error scores. Name error. Scores not defined when running the cross validation. Score not defined. Do you mean scoring or score here? Did you type it wrong? I see. TRAG is actually, we had here, this is the one that we had used. Okay, you could actually do it this way. Actually, yeah, we could do that. So we could actually define it again, right? Okay. All right. Now let's display the scores. Okay. This is the scores that we have computed. Okay. And yeah. So we are just we're just creating our display scores function and going to use that. So these are the scores. Okay. And here, the standard deviation seems to be really low. This is interesting. Okay. And all right. Okay, the mean is okay. The standard deviation is okay. The mean is 71,000. Now this one you can see that this time when we ran it over the cross validation, this time we got a different picture. We got a very different picture. This time it actually went down. It actually went below what we had done earlier, the linear regression one. Okay, so we can also try checking the validation of the previous algorithm. So in this case, the linear regression is giving a mean error of 69,000, while the decision tree regression is giving us 71,000. So which one is better, linear regression or the decision tree? Linear, right? Okay. So let's at the same time, right? Let's also try the, okay, so these are the results so far. These are the results so far. While linear regressor is giving us this mean error, and decision tree regressor is giving us 71,000 as mean error, the standard deviation in case of linear regressor is 2,731, while in case of the decision tree regressor, the standard deviation is this much. So you can see that in case of decision tree, the values are not varying too much, okay? And decision tree is overfitting when we fed the entire data set. When we fed the entire data set, for some reason, decision tree kind of figured out that it could fit or overfit the data, okay, overfit the model. And that's the reason why the root mean square error came to 0, right? So the deviation from the deviation from the mean is lower in case of decision tree, while deviation is more in case of linear regression, but the overall error in case of linear regression was lesser. So cross-validation gives estimate of the performance of your model and also a measure of how precise is this estimate. Okay, decision tree has a score of approximately 71, 379 with a precision of the standard deviation 2458, right? Now let's try another model called random forest regressor. Okay, this is another algorithm. This is another way of regression. Okay, so internally, random forest is basically training many decision trees and on the random subset of the features and averaging out their predictions. We will cover random forest in details in the later point of time. All right, so let's take a look here. A question from Kamal. Can I say if the regular error is lesser than cross-validation error, then it is overfitting? Yes, yes. So, okay. A question from Noor. How do we know what these models doing internally? These are all documented, and we will learn this as part of the course. Okay, we'll learn individual model. And yes, that's right, Kamal. That if the regular error is far, far lesser than the cross-validation error, then it is overfitting. That's right. Okay. So overfitting is when we try to kind of look at a data set and try to fit a complex theory into it, saying all the people whose name start with N ask too many questions. Okay, so like for example, Noor and Nirav, and then we generalize that. Okay, these people are asking too many questions, right? So I mean, no offense, I'm sorry, but yeah, I'm just trying to take a case. So we kind of look at data and try to fit in the theory. That theory does not work out if the data set changes a bit, changes a bit, right? And okay, so basically, basically, when the data set changes a bit, the input data set changes a bit, and suddenly the algorithm doesn't work. And that's when we realized that, yeah, maybe it was overfitting it. Okay, question from Ross. I think the confusion comes from why having to further subdivide the training set to find out it's overfitting. So to find out whether something is overfitting, this is one way. There could be other ways, right? And if you let's say we did not subdivide, let's say we did not train it on 80% first. Okay, let's say we did not train it for 80%. Okay, and let's say it gave us very good results for one part. Let's say, where was the diagram? There was a diagram somewhere. It's a very good point. Thank you, Ross, for this question. It's a very good point. So the confusion is occurring because we our algorithm worked pretty well on the whole training set. Okay. And then we are subdividing it and trying to see if it is working well with how well it's working with the 90% of the data. So let me step back and let's say we did not run it on the whole training set. Okay, and instead we ran on this first iteration. We did this first iteration and it gave us good result because it overfitted it. Okay, and the theory it built for the first iteration gave us an error of 0 here. The chances of that theory not working out when a dataset bit changes, when whatever overfitting we were doing, if the dataset bit changes a bit, changes, so that theory will not work out so well. In that case, the error will be different. Unless the algorithm is really clever and is able to figure out another kind of a theory, another kind of model for for this remaining data set, okay, and so on. So, right, if the algorithm is able to do that for all subsets really well, is able to kind of come up with a model which fits all kinds of subsets, then that means the algorithm is really, really well and it's able to predict, is able to predict really well. Okay. All right. So I hope that explains. Was he able to explain, Ross? Okay. If it's maybe, that means it's not explained yet. All right. So the point I was trying to make is that it just so happened that on the final data set, it was able to do well. But when we gave it a slightly different data set by having the folds, then uh, then it did not work out well. Okay, so that way. All right, let's move on. Okay, now question from Kamal that since it's going to take a lot of time, the maybe we can basically either we can keep lower number of folds. Okay, we could say folds equals to 3, so it will divide this into 3 and so on. Okay, or in the beginning we can divide the test and training in a different way. Yes. All right. But I mean, there are mechanisms now to run the same models on, say, big data platforms, say Spark or other places. The philosophy will remain the same, just that the way we load the initial data, that would vary. Okay, the overall philosophy, whether we are doing the same thing using multiple computers or GPUs, the philosophy, the whole bit of uh, theory will remain the same, just that it will run on many computers or many processors. All right, so that could also be done if it's taking too much time. If your data is really humongous or it's taking too much time, we could go for distributed or parallel computing. All right. All right. So we can change the number of folds, Kamal. All right. All right. So a point from Raj. Uh, but to go from 0 to large error, it was actually quite a jump. It was quite surprising at this point to see error at 0. Okay, good. Let's move on. Okay, so a question from Noor: changing number of folds will not reduce data, it will only reduce iteration. No, actually it will reduce the data. Imagine that we have two folds. What does two folds mean? That we will split the data into two parts, two equal parts. Okay, and we will train on first part and test on second part. Okay, this is what I've understood. So okay, we basically break, because here we are not passing the size of, if you take a look, we are not passing the size of the fold. We're just passing the number of folds. So number of folds means it is going to fold the data that many times. And when we fold something, it's basically we fold it equally. And that's how. Okay, good question from Bintao. That's what is coming next. Okay, all right. All right. Okay. So maybe we can further control the amount of data that we need to pass, and I think that should do. All right, let's move on. So okay, this is where we are. All right, now let's try with random forest. Okay, so here we are defining the just exactly the same way. Here we are defining the random forest, and then we are checking the output. Okay, so in this case, the root mean error is 21,941. This is far better, right? This is far better. Okay, and let's just check with the cross validation how it's going. All right, so here we've run the cross validation with the, it's going to take some time. Okay, so here we have brought it down from 68,000 to 52,000. All right, so you can see that the the overall error that we're getting is now 52,000. All right. Okay. So when we are training the random forest, the overall error is this much. Okay. The overall error is this much. And the standard deviation is also quite low. All right. So here is the scorecard of the three algorithms. Linear regression, the error was 69,000. Decision tree, 71,000. Random forest is 52,000. Okay. Which one would you like to go with? Right? Random forest, right? Good, good. All right. Now, let's explore more models using other machine learning techniques such as SVM and others. Okay. And okay. And we will. The goal is to shortlist a few promising ones. Okay. That's kind of, I mean, that's kind of a to-do list for ourselves. So we should compare the other algorithms. Here, what we're going to do is whatever algorithms that we know of, we will train those algorithms and whatever we can out of these existing algorithms. Okay. And then the goal is to shortlist a few promising models, 2 to 5. Okay. And then use those. Okay. Sometimes what we do is a very important part why we are doing this is not only to compare, not only to pick the best model, we might be using ensembling, as in we can ensemble these algorithms in a sequence that first let's do the prediction based on this and then this and use both of that to get the result. That's called ensembling. We'll cover the ensembling also. Okay, so we'll talk about ensembling in detail later. All right. Okay, so yes. All right, we are now. Let's move ahead. So far, we are very happy with random forest, and let's move ahead and try to fine tune the model. Okay, so we could also try the similar way other algorithms. Okay, so we'll try the other algorithms afterwards. All right, so here we go. Yes, we will refer back to this one as well as talk about other examples. Okay, because ensembling multiple algorithms, instead of using either or, we can use multiple algorithms to solve our problem. And ensembling is very common in case of NLP when we are doing the text processing, or ensembling is also quite popular in other problems, other kind of machine learning problems. So we might take other examples of ensembling. Okay. All right. So next step is to fine tune the model. Fine tune the model, right? The first way is to use different hyperparameters. Okay. Let's try to understand what is hyperparameter. Hyperparameter is nothing but parameter to your algorithm. You remember we passed this random state. This we called a hyperparameter. Okay. So going ahead, let's try to fine tune the model now. So a machine learning model is a mathematical formula with a number of parameters that need to be learned from the data, right? So, many attributes that are fed to the algorithm from the data side. The soul of machine learning is to fit a model to the data by training a model with existing data. We fit the model's parameters to the data parameters. Okay, so that's what we do. Okay, so all right, let me just define what I mean. All right, okay. So imagine that we are doing the linear regression, right? We will uh, try with all possible lines. Okay, let's say this is our points, right? So we'll try with all possible lines. Okay, uh, and see which one is fitting best. This is basically the linear regression. We're going to kind of do this again and again. So linear regression does this, tries all possible line and see that, right? So there could be a scenario where the linear regression is trying to optimize a lot of things. So initial value from whether to start from here or start from here would would also impact the output of the linear regression, right? So most of these algorithms have various parameters, and we don't know which one to choose, which one to choose with. Okay, so that's where we fine tune these parameters which we are passing to the algorithm. Okay, these are another hyperparameters are another kind of parameters that cannot be learned from the model, learned from the data during the training process. These parameters express higher level properties of the model, such as the complexity, how fast it can learn. Okay, so there could be many aspects, because, like, for example, we passed a random number to our algorithm, or number of folds is another hyperparameter you can think of, but we are not passing number of folds to the algorithm, so it's not strictly a hyperparameter, but it is an example of parameter to an algorithm. Okay, so these parameters are called okay, so we need to figure out various hyperparameters for various algorithm. Okay, and we'll just be setting all these variables. So it's like saying this: there was this algorithm which wanted us to set the parameters, and we did not know what to set in those parameters. Okay, so what we did was we are going to try all combinations. Okay, and whatever gives us the best results. Okay, whatever gives us the best result. It's as simple as that. So let's say examples of hyperparameters are number of leaves or depth of the tree in case of random forest, the learning rate, how fast a model should learn. Okay, learning rate as in how fast we should be learning, and number of hidden layers in deep neural network, number of clusters in k-means clustering, and so on. Okay, there could be many parameters associated with most of these algorithms, right? Now let's learn how to fine tune the models. Okay. One solution is to manually fiddle with the hyperparameters until we find a great combination of hyperparameter values. We'll keep changing it. This is a tedious manual work. Okay. And may not have to, we are pretty bad at trying all combinations, by the way. And hence, we go with intuition a lot. So we might skip a lot of combinations. So instead, we use something called grid search. Grid search is basically a program that evaluates all possible combination of a hyperparameter using cross-validation. Okay, using cross-validation. And we need to tell which hyperparameters we want to experiment and within what range. Okay, we will cover grid search in details at a later point of time, but we can just try here. The following code searches for the best possible ones. So here we go. So here what we're doing is we are using grid search. Okay, the grid search, the grid search is taking the name of the algorithm as argument, the parameter grid. Okay, the param. So here this is the important part. So we are telling the grid search that this is the name of a parameter and these are the values to be tried for it. Okay, this is the name of parameter and these are the values to be tried for it. Okay, and this is another parameter, this is another parameter, and this. Okay, so my question is how many permutations it is going to try. Okay, so all right. Okay, so let me come up again. So this is one dictionary, this is another dictionary. Okay, this is one dictionary, this is another dictionary. This dictionary is going to be used here. Okay, and yes. All right, so this and this, or this and this, like that, it's going to try all of this. All right, so we basically give these array of dictionaries. Each dictionary is basically going to be tried once, and then this, then this. So here it's going to be 3 into 4, 12 combination, plus 2 into 3, 6 combination, right? So 6 plus 12 is total 18. Okay, the point I'm trying to do is this is the summation, not multiplication. So it's first going to try this, or and once it finishes this, then it's going to try this. Okay, yes, it's actually, you know, brutal multiplied. All right, let me tell you this. It's important aspect, and we basically, okay, so here what you see is this is another one dictionary, and this is another dictionary. Okay, so first it's going to try these combinations. This is going to try these combinations. Let me see if I could write this code for you. Okay, all right, this is okay. Let me just write it for you here. All right, so let's say here, right? So what it's going to do is it's going to say for I in this, okay, and then for j in this, and say print, I'm going to try this and this. This is how we do, right? Okay. Okay. So it's going to try 3 with 2, 3 with 4, 3 with 6, 3 with 8, and so on. And so, right? And this is going to do it for each dictionary. Okay. It's going to do it for each dictionary. Meaning it'll first try this and then try this. Okay. I'll first try this and then try this. Okay, then it'll basically do another loop here. Okay, there'll be another loop here. It'll look like this. Okay. I hope this clears it. What was the value here? It was just false. Okay. I think this answers the question. All right. So this is what's going to happen here. I hope you got the picture. No. This is 3 and 10. I'm sorry. 3 and 10 here. Okay, so yes, this is what is going to try. Let me put the dictionary at the top so you have the clear picture of what we're talking about. Okay, so the parameter grid looks like this. Okay, so it's going to try this with this, and in another loop, it's going to try this, this, this. So how many total? If we have, say, count equals 0, and we say here count plus equals 1. Okay, and we do that. Oh, we forgot to print count. So total is 18. Okay, so for each of the dictionary, it's going to give it these many shots, right? Okay, a question from Gopi is that why did we separate the two? Okay, why did we separate? Because see, we have a little bit of a hunch also that we would like to try some this, right? So okay, so it basically gives us this of choosing multiple variants. Okay, so it's going to try all combinations here in this dictionary, and then in the second loop, in the second iteration, it's going in the next round is going to try another one. So it gives us more flexibility of trying. All right, sure, I can just okay, any questions at this point? Okay. Okay, so yes. Okay, question from Noor. I think to understand this, we need to understand the internals of model, then we'll know why we are doing this. Yes, so the hyperparameter optimization, basically here we don't know why we are doing 3, 10, 30. Why not 1, 2, 3, right? We don't know why are we setting it 2, 4, 8, 6, 8. Why not something else, right? But here, the point that we are trying to do is that even if we have a rough idea about various parameters, we will be able to try all possibilities. Try all possibilities. Okay. We have no okay. So here question from Balaji is that what are these things? We don't have to worry about it. Okay. It could be as simple as okay, it could be whatever parameters the algorithm wants. Okay, so we looked at the random forest manual. We went to scikit-learn website and we find out that okay, there is this algorithm. There is this algorithm which requires these parameters. Okay, there is this algorithm called random forest regressor, and from the manual we figured out that it wants these parameters. These parameters could be anything between this and this. So we just made a list of all possibilities, right? And then we used grid search over this. Okay, we let this grid search try all permutations and pick the one which has the least error, which has the least error. Okay, so the values of this we have supplied as per our understanding of this algorithm, that we know that random forest needs n estimators. We know that random forest needs another argument called max features, and the value of this could be 3, this could be 10, or this could be 30. The value of max features could be 2, 4, 6, 8, and so on. This much we know about the algorithm. Okay, but we don't know which one will work out. All right, so what we do is we use grid search. So it is still running, you can see that. Now, what we have here interesting is that grid search, okay, grid search is going to use the folding internally. So and on top of grid search, what we will observe is that we will try this with all algorithm, not only with one algorithm. Okay, so total number of algorithms multiplied by total number of parameters multiplied by total number of folds, and then the time it takes for the algorithm itself. So that much is the time that it is going to take for us. Yes, we will learn the details about each of these algorithms later. Okay, all right. The good part is that even if we don't learn in details, you'll be able to use grid search and figure it out by yourself. All right. So yes, we are using the random forest algorithm here. So to grid search, we pass number of folds, we pass the parameter grid, we pass the algorithm, and we pass the on what basis that are we saying that this hyperparameter is working and that is not working. Okay, and then once we are done with that, we call the fit method. Okay, once we are done with that, we can take a look at the result by saying give me the best parameters. So it is telling us the best permutation is max features as 8 and number of estimators as 30. Okay, so We did not have to know the meaning of max features and n estimators to realize that these are the best parameters. So we can use this with the with with the algorithm. Okay, when we are calling this algorithm, we could use this. Okay, now there could be a scenario where we would like to see the estimator also. So here it is showing us the regression only. Okay, and here it is showing all the possible parameters that it has given to the algorithm. Okay, number of estimators for 30 and so on. There are so many hyperparameters that are required for this algorithm. Okay, and we can also take a look at the results. We can, using the .cv results, we can take a look at all the parameters that it has tried and how much error did we get. So best was this. Okay, where was this? Yeah, this one. I think this one was the best. All right. A question is, what does CVRES does? Okay. Right. So the output of CVRES is not very friendly. So we have basically written our own loop on top of this to print it. Okay. All right. Let me also explain some more things related to it. There was some more things that I wanted to explain. Okay. So it's going to try 18 combination, right? This is 18, correct? Let me just see. It should be 18. Yes, 18. Okay. All right. Okay. Question from Kamal is, why did grid search best parameter did not show other params? It did show, right? You have to take a look at the results. It just showed us that only this combination is good, right? I hope this results will give you the answer. This one is not doing good here. Okay. Out of all the combinations, if you take a look at this, right? It tried all combinations that we have provided it, and you can see that this one looks good. No, this one also looks good. Sorry, this one looks better. Okay. Yeah, you're right. Thank you, Balaji, to point that out. So this one is the one that is looking good, looking the best out of all. And I think that's the suggestion. It has given max features 8, number of estimators 30. No. Oh, here. Sorry. Yeah, thank you, Abhinav. Yeah, this is the one that is best. Okay. A question from Noor. For the bigger data set, does this function grid search give the option to use distributed computing? I think you can use multiple cores, multiple CPUs with grid search. Also, the libraries like MLlib, they provide you this functionality of dividing the grid search on the cluster. A question from Binta, how to find the explanations of parameters? The best way is just take a look at the scikit-learn manual. That one is probably the best way to look at. So this one, the first one itself generally comes as scikit-learn. This is the one, it'll show you that these values are there, right? Okay. So you can just take a look at the manual if you are in hurry, so you can take a look at. All right. So this is how we did the grid search. Okay. Yes. All right. Now it doesn't end here. We are going to do some more. Okay. The next is, oh, ouch. We are already running out of time. All right. So the next is random search. Okay. Um, in case of grid search, the problem was that we are exploring relatively few combinations. When the hyperparameter search space is large, we can use randomized search CV. We'll cover randomized search CV in details at a later point of time. What we do is basically, instead of trying all combinations, it evaluates the given number of random permutation, just picks up few of the random ones and do that. Okay. All right. So yeah, we'll cover this maybe in the next session. We are almost towards the end, and we'll just have another thing called ensemble methods, and then we'll have finally we will do the run on the test method. Okay, that's pretty much, and we will talk about presenting the solutions later. Okay. All right. So yes. All right. So we will start from random search next time. Okay, let me give you this link. This looks good. All right. Yes, we'll update the slides. Okay. Okay, and the diagram. Good. So that's pretty much for today. A question from Kamal that instead of, I mean, along with fine tuning and the other models, maybe if we used better combination of data, it would have given the better prediction. Is that not possible? That's very much possible. Okay. Tanmoy's question is, so are we having class next week? Yeah, I'll just send you an email, and I think a better way would be that you give me a quick response. Okay. All right. All right. So great to have all of you in the session. Wonderful set of candidates we have in the class, and I'm thoroughly enjoying your question. Okay. All right. I look forward to see you next session, or maybe next. I'll confirm the next time. Okay. Okay. All right. Noor's question is, how much course have you covered so far? Question is, how confident do you feel what we have learned so far? Okay. Can you start doing a project now? After this, we are planning to give all of you one project each. And yes. So, okay. All right. I'll do two things. One is regarding the next session, and second, I'll drop you an email about the projects. I think we can start the projects now. Okay, let me commit my classwork. Okay. So I've committed it to the GitHub repository. You can take a look. Sure. Sure, Noor. All right. All right. Okay. Thank you, everyone. I look forward to see you as soon as possible. Bye-bye. Have a good day.